Assalamualaikum guys, this is Najmuni Shah. Today came to explain you about the new chapter, the shape of the orbital and quantum number under Unit 1 atomic structure. Let's move on to the continue. So actually, according to my presentation, I used to mention you all when we going to study anything before that, we should have an idea about what is inside this presentation, what I'm going to start, right? From that motivation, we will start the first thinking, what is that? The shape of the object. Okay. Still in your O levels, you just study about the number of the electron shell and everything, right? This is the configuration, everything. But hereafter, we are going to step into the new that is the imaginary electronic vision, right? So according to that, you should have the electronic vision, right? That is what we are going to speak, the shape of the orbital. So next is the orbitals and quantum numbers. So on the orbitals and the quantum number, there are four things that is you should know that one definitely. The first one is the principal quantum number. It's called N. And second one is this angular momentum or azimuthal quantum number. That the symbol is L. Next one is the magnetic quantum number. You can say it is ML. The final one is the spin quantum number. It's MS. Let's move on to the first head. The shapes of the orbitals. Whenever we speak about the shapes, how can define about the shapes? Yes. An electron's probable location in space around an atom that shows the shapes of orbital. It shows us the electron density is distributed around the nucleus. Simply you can say how you can define the shape, how the electrons is surrounding, what that means the electron density is distributed around your nucleus. Or how it's the location, the probable location of the electrons in your space around the atom, that is called what? The shapes of the orbitals. Right? So when we speak about that, we have the different orbitals here. The first one is the s orbital. What is happening here after you will study about the electron configuration according to this orbital? So you have the different three type of the orbital. When you take that one, there are s orbital, p orbital, then d orbital, final one is the f orbital. Actually, under your O-level syllabus, right, we are studying here, even though f orbital is under its orbital condition, you should able to know the shape of the s orbital, p orbital, d orbital. D orbital also we are not studying that much in detail. F orbital shape is you don't need to think about that. So now when you speak about the s and p orbital, right, and d orbital, just without that I will show you how the orbital is aligned. Okay, so the s orbital is always what? The spherical shape, right? Spherical means what? This is. And when you take the p orbital, right, I will take another color. Yes, when you take the p orbital, is always what we are telling, the dumbbell shape, right? When you step into the d orbital, right, that is what we are telling is double jumble. That's all, right? Okay, so undo. So the node should be like a flower. This is what we are called the g orbital. F orbital we are not studying here. So according to that, how they are defining this is the s orbital, p orbital, d orbital. This is because of what? The space around an atom, right? How the location of the electrons, that is what we are telling the shape of the different orbitals. Let's we move on to the subject now. So what is telling is the electron density for an s orbital is spherically symmetric and concentrated on the nucleus, or in other words, s orbitals are spherical in shape. This is what you have to know. So spherical in shape. So can you see, right? The 1s, 2s, 3s. What is mean by that? It's always the s orbital is spherically symmetric one. It's concentrated at the nucleus. Or another word you can say it's a spherical in shape. The distance, the width is increasing according to that what the number of shell increases. So this is what the shape of the orbital, s orbital, that is spherical in shape. And next one we are going to speak about what? The p orbital. The p subshell has 3 orbitals corresponding to the 3 allowed values of ml. You will study the quantum number, then you will understand what is mean by the ml. So here you will have the -1, 0 and +1. And the electron density is not distributed spherically as in your s orbital. So you should be very careful. I will use the annotate here. Right? When you speak about the s orbital, okay, s. When you speak about the s orbital, it is what the spherical in shape. You will have only the one orbital, right? But if you speak about the p orbital, we are speaking about what? The ml. What is that? Is the azimuthal number. We will study after. So you will end up with what? So you will have, this is we are telling 0. Then you will end up with only 3 orbital. Right? I will use the text. Okay, so only 3 orbital. This is what I'm speaking for what? Yes. So when you take for p orbital, you will have what? The ml is equals to +1, 0 and -1. So if you have such like this +1, 0, -1, we are telling the number of orbitals are. The number of orbitals are 3. So right. So this is belongs to what? Your p orbital. So you should be very careful about that. So this is what we are telling is the shape of your p orbital is shape. I need a space. Again, right. Right. Okay, you know the dumbbell which we are using for the weight purpose. This is what we are telling the p orbital. Right here, the p orbital is not concentrated like the spherical in shape in the s orbital. You have the 3 subatomic orbitals, right? I said one is the +1, 0, -1. According to that, the p orbital having the 3. The s orbital is having only one orbital, one suborbital. So let's see the shape of the p orbitals in clear view. So instead the density is concentrated to the 2 region into on either side of the nucleus is separated by a node of the nucleus. So the dumbbell shape orbital has 2 bonds. So this is what for the each values of n, the 3p orbitals have the same size and the same shape but differ from one another in spatial orientation. Therefore, it is convenient to label these as Px, Py, and Pz. The orbitals were later. Subscript indicates the Cartesian axis belong to the orbital in orient. So actually, I already said about these things, right? When it's not concentrated like your spherical in shape, that is having the two region in the either side of the nucleus. It is separated by the node of the nucleus, right? They said. Therefore, you can see two lobes that orbital is shaped what the dample shape. The each n value you have the three orbitals the same size that but the shape and same size and shape, but the differ from the spatial orientation. Why it is getting for that sake, it's getting the Px, Py, and Pz. Let's see that diagram. Then you will understand why they are telling like that. The shape of the p orbitals. You should be very careful, right? When you see this guy. So I said why it is the concentrated in the either side. The electrons are concentrated this either side, right? This side and this side, okay? It's concentrated either side. It's separated by the node, right? The nucleus at this node. And we said the 3p orbitals is what? The same shape and the same size, but it differ according to that the orientation of the free space. So according to that, when you set the pz, we used to draw the orientation. The axis, this is what z, right? Okay, and the axis, this is what x. Okay, and the axis, this is what y. According to that, which is line to this z axis, we are called what the p set orbital. If it is lie into along to the x axis, we are calling the px orbital. Finally, if it is lie to the y orbital, y axis, we are taking the py orbital. This is the variation. The shape and the size are same, but it's differ according to the orientation. This is what we are called the p orbital. So the different d orbitals given the shell have the different shapes and the orientations. So this is what we are telling is a complicated shape. The shape of the orbitals are even more complicated than those. The d orbital we are telling is a double rumble shape. So this is we are not studying under L section. So until now we studied the shape of the orbitals. Now we are going to study about what? The orbitals and the quantum number, which is very important, and you should have the electronic configuration vision box along this. The first thing, the Moore model introduced a single quantum number is called n to describe an orbit. According to this, the quantum mechanical model used three quantum numbers. What are they? N, L, M, which describes an orbital that electron occupies in atom, and ms describe the spin of the electron. You should be very careful about that. So what they are telling is, right? So when you take the quantum mechanical model, right, the quantum numbers, what they are using is n, l, and ml, right, which is describes about what your orbital, how the electrons occupy in an atom. So you can say the orbital, how electrons occupy. But when you go for the ms, speak about what? The spin of the So this is the variation. These four things we are going to study. These three, what is explaining about the orbital, how the electron occupies in the atom, and ms shows by what the spin of the electron. So this is what we will going to study one by one. So that is very important, and let's we move on to the first principal quantum number. So the principal quantum number is described as an n, right? So what it says is it can have the possible integral values. So n means, you know guys, whenever we speak about the n, right? I'll go for the next one. The quantum numbers defines the main energy level. You can say what the electron shell. Right? So it says about what the main energy level or the electron shell that the electron occupies in the atom. So simply you can explain what this telling is. The principal quantum number is your number of shell. Right? Now you have 1, 2, 3, 4. Therefore your n is equals to 4. That's all. So always your principal quantum number will have the possible integral value. So that could be 1, 2, infinite, whatever. And it explains about what the main energy level, that is your electron shells. Right. And next we will go to what the second quantum number is. The angular momentum or azimuthal quantum number. Azimuthal quantum number, we are telling that is L. How you can define the azimuthal quantum number? It can have the integral value. You should be very careful about that. I should have. Need to use this. Right. The integral value should be what? The 0 to n minus 1. Though you say if your n is equals to 4, what is your azimuthal quantum number? Your L is equals to, yes, 0, 1, 2, and 3. Why? If 0, the L is equals to what? The integral value 0 to n minus 1. If you say the n is equals to 4, that value should be what? 0, 1, 2, and final one is n minus 1. That means the 4 minus 1 should be 3. This is how we are going to find the integral value. And what it says, the angular momentum or azimuthal quantum number explained about the shape of the orbital. It clearly says about what? The shape. So from this, if it is saying about the shape of the orbital, you can define either it could be what? S orbital, p orbital, d orbital, and f orbital. So now with this, okay, you will get the value according to the L is equals to what? From 0 to the n minus 1. You will explain the shape of the orbital belongs to that. So you will be clear. Okay. So therefore, we are telling if L is equal to 0, that should be S orbital. If L is equals, if L is equals to 1, yes, that should be p orbital. Yes, what should be next? Your L is equals to 2. What is the value? That should be what? d orbital. Then your final one is L is equals to 3. This is what F orbital. So we are studying until the F orbital, so you won't get to know about that. So according to that, if you're able to find the N is equals to the value, so according to this, you can define the shape of the orbital. So let's have an example, right? If you say I'll use another color. Okay, we'll go. Okay, according to this, let's move on to the next example, right? Okay, so we will have another one. If you say n is equals to 3, can you say what is the L value? What is the shape of the orbital? By using the azimuthal quantum number, you can define the shape of the orbital. Then you can see if you said the n is equals to 3 and L is equals to 2. What is the shape of this orbital? How can you name this orbital? That is what? 3, y, n is equals to 3 and L is equals to 2 means what? You will have the d orbital. So there. This is how you have to design the shape of the orbital. Right. So let's move on to the theory is given here. So what is meant by the angular momentum? We can have integral value from 0 to n minus 1, the each value of n. I said. So the quantum number defines the shape of the orbital, right? Either so it could be what? SP, D, or F. So if it is getting the S orbital, it should be 0. If it is P, it should be 1. If it is T, it should be 2. If it is F, that should be 3. Right? According to that, the set of orbitals have the same n value. So that we are called what? The subshell. So how can you name the subshell? By naming that designated number, that is for what? Is a value of n and the letter SPD for what? From that you can define the subshell. So for an example, I said when you take the 3D subshell, how it's defined is n is equals to 3 and n is equals to 2. This is how we can find that. So let's move on to the next. The third quantum number is ML, the magnetic quantum number. So what is mean by the magnetic quantum number? Before that, you should have an idea about the integral value. The magnetic quantum number. Yes. So always the integral value should be what? The minus L2 plus L. Right. Okay. So what this magnetic quantum number explains? The orientation of orbitals in space and the number of possible value of L denotes the number of orbitals in the subshell. So you should be very careful about that. What this L says, the orientation. Yes, the orientation of orbitals. And also it explains about what? The possible values of L denotes to the number of subshell, the possible value of the subshell. we have an idea about that, it should be clear to you all, right? When you speak about this, your L is equals to 0. Right. We said that is what S of it. Therefore, what is your MS? The orientation orbital and the possible values of the subshell. The S will have only one subshell. And if you go forward, the L is equals to 1. Right? You know what is that? It's P orbital. And you can define what? Yes? You will have the L is equals to what? The minus 1, 0, plus 1. Therefore, you will have the 3 subshell. Next, L is equals to 2. That is D orbital. And it will have what? Minus 2 plus, minus 1, 0, plus 1, plus 2. Therefore, you will have the 5 subshell. And finally, your L is equals to 3. It will denote to the F orbital. And what is the value? I said, yes. You will have minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Therefore, you will end up with 7 subshell. So, this is what your magnetic quantum number says. So, you will end up with this. Okay, I will use another color to show the, right. So by this way, you will be very clear about that. We will have the next last page. We have that relationship between the principal quantum number, azimuthal quantum number, and the magnetic quantum number. Then you will realize how it's going. Okay. Now we will go through the notes. So I said, when we speak about the magnetic quantum number, that is therefore ML, it can have the integral value between the minus 1 and the L, including 0, right? So therefore, the quantum number describes the orientation of orbital in space, I said, right? It explains about the orientation. And the number of possible values for L denotes the number of orbitals in the subshell. So according to that, you can describe about the number of possible subshell under the orbitals. When you take the example, if you say it's L is equals to 0, you will have the possible value under ML is 2, 1, 0, minus 1 and minus 2 that denote that these subshells have 5 orbitals. So next, the fourth quantum number is MS, that we are called the spin quantum number. MS. So this is what. Here we are talking just the spin of the electron. This is what we are talking here. So this is what they are telling under spin quantum number is there is only 2 possible values allowed. It can be either positive half or negative half, which is indicate the 2 opposite directions which the electrons can spin. Should be very careful about that. The word is explaining very clearly. The spin quantum number says what? Where the electrons can spin the opposite direction, it could be either positive half or negative half. From this, a spinning charge produces magnetic field. These two opposite direction of spin therefore produce an oppositely directed magnetic field. So here we just talking about what? The positive of the negative of the spin of the electron. It's always the opposite direction. Therefore, it is able to create the magnetic field. Those magnetic field also directed what? The opposite field. Right. Special note. The total number of orbitals in the shell is n star when the n is the principal quantum number of the shell. If you want to find, right, if you want to know the what is the total number of orbitals, the total number of shell is present in the particular orbital, how would you find the total number of the orbital? We'll see. If it is the n is equals to 3, so we said, how would you find the orbital number? N star, 3 into 3, that is 9. If it is 4, yes, 4 squared is 4 into 4, that's 60. So let's move on to the relationship between the values n, l and m. Then you will understand what I'm saying. This is clearly I will explain you. Just keep on your eyes. Right. When you take the n is equals to 1, right, your possible L value, we used to, I said, right, yes, the n should be what? 1 minus 1. For that sake, it's become as a 0. If it is 0, we are telling the shape of the subshell is what? 1s. And the possible value also what? Is 0. So if it is 0, 1s, the s orbital, therefore the number of orbitals in this subshell is 1. The total number what? 1 squared, right? If you have this. 1 into 1. So you will end up with what? So 1 squared, that is 1. And we'll go for the 2. We said, how would you find the L? Yes, it's 0 to n minus 1, right? When you take the 2, right, when you take the 2, you will have 2 minus 1, which is equals to 1. So you will have what? The L value is 0 and 1. So therefore, it will get what? Yes, 0 value. So if it is 0, that should be 2s, and the possible destination should be 1, 0, the number of orbitals of shell 1. And if you go for what? Yeah, it could be have the 2 minus 1, therefore 1. Okay. 1 is for what? You have to write the ml value. The 1, it means it's a second one. Therefore, we are writing as a 2p. And p cell will have what? The minus 1 including 0 to the positive L value. So therefore, you will end up with minus 1, 0, plus 1. So you have 3 here. Therefore, 3 subshell, the 1 plus 3 is will giving the 4. You know, when you take the number of this n squared value, the number of total shell you can give, that is 2 into 2. Then you will end up with what? This 4. And next go for 3. Again guys, you have the clear vision on that, right? Okay, look at the 3. Now you have to find the L value. L value is what? 0 to L n minus 1. Therefore, you will have 0, 1, 2. If it is 0, that is S, and this is what the number of shell, the principal quantum number is 3, therefore 3s. Always the possible value for L is 3s is 0. Therefore, this is 1. I just keep this happy. And we'll go for the 3p. Why? If it is 1, it's a p. And P always will get what? The minus 1 to the plus 1, including 0. So therefore, this is 3. And go for 2, right? You will, if it is 2, we are telling that is 3D, right? So D means what? The minus 2 to the plus 2. You will have 5. If you add all together, you will end up with 9. So that is, we can say 3. And this is also 4. How the total number of shell came? 4 square. And if it is what? 10 minus 1. So you will have 0, 1, 2, 3. If it is 3, that is F. If it is 2, that is D. If it is 1, that is P. If it is 0, that is 1. And this is belongs to according to the principal quantum number. And according to, if it is S, the M value always 0. If it is P, you will get the minus L 2 plus L, that means minus 1 to plus 1, including 0. So you will end up with 3. And this is for D, minus 2 to plus 2, including 0, you will end up with 5. And if it is F, minus 3 to plus 3, end up with 7. Altogether, adding that, and you will get what? The 60. This is what this chart is very important, and once you go through you will realize, and it's really easy. And there was a questionnaire, and go through and try to do that question by using this chart. Definitely you all can do this, right? Yeah. And thank you very much, guys. I have completed the principle, the shape of the orbital and the principal quantum numbers, which is under the quantum orbitals, right? So let's meet on the next new chapter. Until that, see you. Bye-bye, guys. Take care. Assalamu alaikum wa rahmatullahi wa barakatuh.